As a data scientist, you kind of wear many hats. Mathematician, statistician. In the current section, I want to discuss briefly, computer programming or being a computer scientist, computer hardware. So again, everyone probably is familiar with this, right? A computer, also sometimes called a server, is composed essentially of hardware and software. The primary hardware components of all computers are kind of shown here. They all have power supplies, they all have motherboards, they all have CPUs, RAM, GPUs, and hard disk. And of course, they have some way for humans to interact with them. Usually, this is kind of optional. Some computers, are rarely interacted with directly by humans. They're usually interacted with through a terminal, which I'll discuss more later. And of course, they have operating systems, often, of course, Windows, but also Unix-based systems such as Mac OS and Linux. And then within Linux, there's many distributions such as Ubuntu, Red Hat, CentOS. There's just literally dozens and dozens of them. And of course, the programs that make up the computer are written in various computer languages: C, Fortran, R, Python, et cetera, et cetera. Serial computing, this is just kind of an analogy, like a fun analogy, but it's kind of helpful to think about things this way. If you think of the groceries as analogs of data, so those are basically bits, zeros and ones stored in the computer in some way. You can think of the cashier as the CPU, the processing core, so this is what does the work. So this crunches numbers, it does mathematical operations and Boolean operations, so this is kind of the brain of the computer. And also there's a specialized processor, so this is called a central processing unit, but there's also called a graphical processing unit, which does all the visualization, so that makes your screen, basically makes your screen work and renders the graphics. These are highly efficient at linear algebra operations, whereas the CPUs are kind of general computing devices. These can do sort of any kind of computation, where these are more limited, but much more specialized and much faster for linear algebra computations. The cart is kind of like the hard disk. So this is sort of long-term storage. So like you would store the groceries here for an extended period of time, and then when they're ready to be processed by the processor, they get moved from the long-term storage to the memory, which is also the RAM. So again, the belt is kind of like the analog of the RAM. And so things need to go, they kind of just sit in the cart. They don't really do anything there, but they can sit there for like extended period of time. But then when they're ready to be used, they get moved to the RAM, and then they get processed by the processor. And the long-term storage is held on disks, so hard disk or solid-state drives such as flash drives, and then the RAM is much faster access because it's closer to it's sort of more optimized to be send data to the processing unit. And so of course, like again, this is kind of silly, right? Of course, we have desktops and laptops. iPhones and tablets are essentially the same thing. They're just different form factors. So they have the same fundamental units. They have hard disk, they have RAM, they have central processing units, etc. And also, there's this kind of fun. There's these Raspberry Pi devices where, again, same thing. They have CPUs, RAM, etc. And these are kind of sort of nerdy, fun things if you want to play with them. But you can actually interact with electronics. So you can like program all kinds of fun electronic devices. For our class, probably one that you might not be as familiar with is a rack server. So these are usually Linux machines, and they're just a different form factor. So if you open it up, it's completely identical to a desktop. It's just flat so that we can stack them. This is an example of one. This is actually one that I bought off of eBay in the fall. It's a Dell PowerEdge, which is a popular brand of server. A lot of computation is done on PowerEdge computers, and this is an old one, so I was kind of being cheap, so I bought one off of eBay. But it's still it's probably 5 years old or so, maybe a little older. But it has 24 cores, so it's a decent amount of computational capacity and a small amount of RAM. If you open up the lid, again, it's just very similar to what you'd see inside your desktop or any other computer. If you open it, it's got a power supply, like I mentioned, space for the disk. So these slots, you can put a whole bunch of different hard disk in there. So that's long-term storage. Again, that's where data gets stored when it's not being used. When the CPUs want to do something with the data, it gets shuffled to the RAM. So these are the RAM slots here, and this has 2 CPU, each of which with 12 cores. And so again, this is like short-term storage where the CPU can very quickly access it, and it's all about computational speed. So like it's slow to communicate data from the disk to the RAM. It's much faster to communicate from the RAM to the CPU. So all this is for computational reasons, to accelerate computation because we don't want our code to run for days when it could run in minutes, right? It's always the faster is better, basically, when it comes to computing. Supercomputers there's nothing magic about a supercomputer. It's just literally hundreds and hundreds of computers connected together with either Ethernet cables or more commonly InfiniBand, which is kind of an analog of just a faster version of Ethernet, and other ways to connect them. But they're basically computers connected together. There's a switch that controls communication between all of them, and they're usually connected to the internet in some way. Usually, it's common for supercomputers to have this kind of architecture where there's a master node, and this is kind of what you access when you log in. So your computer's out here. You'll typically do what's called SSH, which is a command line. It's command on the command line, and you can get inside this head node from outside, and then that gives you access to the entire cluster. And these are called compute nodes, or sometimes called slave nodes. And these are like the workers. So like you get inside of this one, you tell it what to do, and then there's a queuing system that distributes your job to all these different computers or segments of it. It might claim these first 10 computers and do a bunch of work on them, whereas some other user might be using these 20 computers or whatever. And again, these are usually composed of rack servers. So again, it's just a whole bunch of computers, typically in this form factor of the rack server, stacked on top of each other, connected together with switches and cables and whatnot. And supercomputers are expensive, of course. So like a lot of times, it's government agencies will host or manage these supercomputers, or large companies like Amazon and Microsoft. Parallel computing. So back before the early 2000s, so in the 90s, the central processing units, the CPUs, only had one core, so they're single core processors, which means they could only do one line of work at a time. So they were very slow. You can only do one thing at a time. Since 2000, we start to see the emergence of multi-core machines, so dual-core processors, quad-core, and now 16-core is common in laptops. That computer that I showed, that rack server has 24 cores, so it's like a grocery store with 24 aisles or checkout lanes instead of just one. So again, in theory, it'd be 24 times faster than a single core machine. There's kind of two paradigms of parallelization, shared memory computation, and this is very common on your laptop. So what it's doing is breaking the job up on the level of the algorithm, either using OpenMP, which is a CPU, it is basically using your CPU, or using CUDA, which is multi-threading on your GPU. So it kind of breaks your algorithm into chunks and sends chunks to the different cores of your CPU, and then it does each chunk independently, and then it recombines it. So in theory, if you had 6 CPU cores, the algorithm would be 6 times faster than if you only had one CPU core. And then there's also distributed memory, which means that there's a whole bunch of, this is kind of like supercomputing, where you have a whole bunch of computers, but they don't have the same RAM. So this computer has its own RAM, this computer has its own RAM. They might have this access to the same disk, so they might be able to grab data from the same disk, but they don't have, like, the processors see different chunks of the data. So this is called distributed memory parallelization, and this is more like MPI, which stands for message passing library, or message passing interface. And so you basically break the job up into, you kind of send your data to different parts, to different computers. They chug for a while, and then they communicate back to the master node, or communicate between each other. So Hadoop is when there's very little communication between these compute nodes, and then MPI is where there is some level of communication. So they're sending, while they're doing their work, they're also sending signals to each other and communicating. And so yeah, you're kind of breaking the job up on the level of the data. Cloud computing is very similar to supercomputing. So, like, again, you have these server farms, which are, again, basically like supercomputers, lots of rack servers connected together, and you get inside through a master node, and you have these users which are kind of interacting with the computer through their laptops. But then the server itself has all these sort of very nice pre-built packages or pre-built applications that it can do. And so again, this is more we'll discuss in 502 if you're taking it. So this isn't the focus of this class, but it's good to be aware of. It's kind of elementary computer science. Why do we care about computation? So this is like a very simple example of NumPy, which does hyper-threading. So if you can watch what your CPUs are doing. In this case, this is just a screenshot, but usually you'll have many CPUs here. So for instance, if you're on a 4-core computer, you'll have 4 CPUs here. If you run NumPy, you'll see all of them jump up. So the computer will start taking advantage of all 4 CPU cores. And so NumPy is highly optimized for multi-threading. So like there's this kind of simple example where you do a for loop. So you just do a whole bunch of, you build some big matrices and then you add them together, I believe. Yeah, you add them. And if you do it with NumPy, it takes about 2/10 of a second. But if you do it with for loops, it takes about 10 seconds, which is about a 600 times speed up. So that's kind of like an insane level of speed up. If your algorithm can be 700 times faster, I mean, obviously we all would rather wait for a second as opposed to 10 seconds. And this is just a toy example that, it scales to many problems.